Hey, welcome to the next part of integration, part 4, using substitution. Don't know what that's about. Let's find out. Have a look at the screen and look at this red hot question here. Are there any other rules we can reverse? And I've got some suggestions for you. Can you reverse the product rule, the quotient rule? Do you remember these? When you have two functions multiplied together, then it's the derivative of the first by the second unchanged plus first unchanged by the derivative of the second. And over here with the quotient, two things divided, it's over the square of the denominator, and it's the derivative of the top function, numerator, by the bottom unchanged, minus top unchanged by the derivative of the bottom. Very similar pattern there in that top line to the product rule. That helps you remember it. But gee, that'd be pretty hard to reverse, wouldn't it? What about this one down here? What's this? This is the chain rule. Hey, you remember that? When you have y is some function in u, and u is itself a function in x, then the derivative is dy by du by dx. Oh, do you remember that? Something like, what could y be? Y could be x squared plus 5x to the fourth. And then dy by dx is, let's do this function here, g, first of all, leaving u, the other function in x, unchanged. Do you remember this? You don't touch that. You do the x to the n rule, and then you multiply by the derivative of what's in there, which is 2x plus 5. It's a chain of derivatives. There it is, and there it is, and here it is, and here it is. Do you remember that? So, do you think you could reverse any of those rules? Take a guess, and then I'm going to take it down below here and see what you think. Let's have a look. Here are some functions. Now, let's have a look through them. Do you think you can actually do any of these integrals from reversal of a rule? What do you notice? Okay, have you seen it? Well, here is one. Have a look. It's got two parts, hasn't it? It's not the product rule, because the product rule produces two products added. Certainly not the quotient rule. What about this one here? Oh yeah, I think I can see a chain here. Okay. What about this one? Yeah, same thing. Function of function, and its derivative is there of the inside function, if you like. And also this one. The function g would be e, and u, the function inside, was x squared, so that's a derivative. Can you see that these are special? These are not able to be done as they stand, because here's a function g, if you like, done on cos x, but the derivative isn't present. So we can't actually reverse that one, because if you can't reverse and do integration if you can't identify the process of differentiation that produced it, because integration can be thought of as anti-differentiation. What about this one? There's a function done on a function in x, but there's no derivative present. This one's derivative should be in there, shouldn't it, if we're going to try and reverse the chain rule. So we couldn't actually do that one except if we expanded this to the fourth here and brought it back to an identifiable rule like the x to the n rule. And down here we've seen those before. Cos squared, we can convert that using the cos 2x formula. Okay, so what about those? Interesting, isn't it? But you must be able to identify the rule which produced it before you can reverse it. Okay, so we have a bunch here. We have a bunch here which we could integrate. Now's the challenge for you. I'm not going to show you how to integrate it. I'm going to say to you that when you use this rule, you get a result, dy by dx is dy by du, the first function, times du by dx. So, if we've got du by dx, and there it is, let's just tidy this one up a bit. We've got dy by dx there, du by dx, sorry, and that's the derivative of that function in there. What was our original y function? That's what we're saying. We want to reverse it, the integral. Okay, so if we reverse that, what was the function? Well, let's increase the power by 1 and divide by the new power plus c. Why am I doing that? Because the y function here is the fourth power. This is the u function here, if you like. So we have to integrate, here it is over here, integrate dy by du. So that's a power function. So we increase the power by 1, divide by new power. Don't touch u. And then we normally multiply by u, but that's already there. So all we have to do here is really reverse this. This is the indicator. Is that the answer? Let's check it. So checking it, the derivative of this piece here is, let's put the fifth out the front, and then it's 5 by x squared plus 3x to the fourth times by 2x plus 3. Okay, that cancels, and the derivative of a constant is 0, of course. Hey, it worked. We got the function back again. What's it saying really? That is that we don't have to worry about this up here. We can virtually ignore it and say it's come about over here by the chain rule, and we only have to reverse this part of it. Okay, and the way we write that is going to come up later on. I'll do it in the formal way in a minute. Well, we said this one can't be done, because that's not a reversal of the chain rule. What about this one here? Has it got the pattern? Yeah, well, if we thought of that as u, and this as y as a function in u, this is du by dx. So we should be able to just handle this part and reverse it. So let's increase the power by 1 and divide by the new power plus c. Don't forget the c. When we check that out, the derivative would be, okay, the 7 stays out the front, then it's 7 by 2x plus 3 to the 6. We're doing this function here now, this idea of the 7th, differentiating that with the x to the n, and then multiply by the derivative of what's in the brackets, which is just 4x, the 3's got 0 derivative, and the constant's got 0 derivative. Hey, it works. What are we doing? We're actually reducing the problem. We're saying the integral of dy by du times du by dx with respect to x is equal to the integral of dy by du times du. That's our theorem. It's really saying that because this derivative is here, we only have to reverse the first one. See that? We only think about that y function as with respect to u, where u is the thing in here. We're taking that as the variable now. Let's do another one. Well, maybe I should pause here and say, well, can you spot what we're doing here? All right. What is u and what is y? You might pause the presentation and have a go at that one and this one over here. The ones that we reckon follow that pattern. All right, let's have a go now. If y was the squared function and u was sine x, is this du by dx? Yes, it is, isn't it? You've got to know your derivatives though. Derivative of sine is cos. So therefore, integrating this, we could just deal with this here, increase the power by 1 and divide by the new power plus c. And then checking it, let's check it again to make sure you're happy. The derivative would be that third and then multiply by 3 sine squared x, dealing with this function here, and then multiplying by cos x, which is the derivative of that. So it does come back to the same thing. And have you got the idea? We're going to set it out a bit more formally later on. It says in the syllabus that you should be able to do this by inspection or by substitution. So you can just use inspection, like that's what we're doing now. So here, there's our function y, and it's done on u, and that's a derivative of u with respect to x. So let's do the integration of y. Integral of e is itself plus c. So that should be our answer, just like that. Okay, let's do a check to get the derivative. The derivative of e is itself, but then we must multiply by the derivative of the power, which is 2x. Okay, and therefore, oops, we don't need a plus c on differentiation. Derivative of the c is nothing. So here it checks. All right, are you getting the idea? We're looking now at reversing the chain rule. So we're looking for a chain of derivatives, and then we're going to identify y and u. So that's why it's called substitution. Let's come down and look at the formal statement, where I've already given you. So if you have y as some function in u, and that u has got an x in it, then the derivative overall is you differentiate the y and keep this as like a single variable, so it's differentiating with respect to u in fact, and then you multiply by the derivative of that u, that other function living in there. So this is a composite function analysis again, chain rule or function of function rule. You need to identify the pieces. So here's our formal statement. If you have the integral of some function f, and it's got a u in there as a function in x, you have got this pattern, f of u, and then its derivative with respect to x. Then all you have to do is integrate the f as if this was the variable. So you can ignore what's in the brackets if its derivative is accompanying it. Derivative is accompanying that function. It's a product, in other words. It's not come from the product rule though. Product rule produces a much more complicated expression than this. This is from the chain rule quite clearly, two derivatives there. And it's a chain of derivatives if you like. All right, let's come down and have a look at how we do some problems now. Just a short presentation, this one. Use substitution to find the integral of this. So first of all, let's set it up. Do we agree that it can be done with substitution? Let's check this here. Yes, that is du by dx of this function in here. So what have we actually got? We can say at this point, therefore, let u be su plus 2x. So u is the function whose derivative is present. Okay, so you actually probably try to identify this as a derivative first, and u is the function, not that, but u is the function whose derivative is present. Then you write down du by dx is 3x squared plus 2. Then you can encode the original statement, because now it's root u du by dx, or u to the half du. You're saying now, in going from here to here, using the reversal of the chain rule. That's what we're saying. That's our formal statement, really, about using that theorem as chain rule reversed. We're saying, hey, can you see that that has been produced by the chain rule, and we only have to do this. So you increase the power by 1 divided by a new power, and divide plus c, and then dividing by this becomes invert and multiply. And then we always return the x expression. We've introduced u to solve and to prove the solution. Okay, now you can go straight to it by inspection. If you can spot that, you can go down here by inspection and not put all the u's in. But you've got to watch it. If it says show that, or they suggest algebraically, you have to show it. And also, it's safer to do this way, you'll see in a minute, when the full derivative is not present. We'll have a look at that in a minute. let's have a look now at these two. So over here, we've got 3x squared plus 2 over x cubed plus 2x. And notice here, not a bad way of doing it is to separate it as a product, so that we're identifying one is a function and the other one is a derivative. Okay, so we're identifying that. So you will look at this and we say, gee, yes, that's a derivative of this function down here. So let u be the function whose derivative is present, not the derivative function itself. Okay, so here it is here. So now we can encode it. So what we've got is 1 on u, derivative present. Therefore, all we have to do is integrate the 1 on u with respect to the u, treating it as a single function in that as the variable. Okay, and what is that? That is ln mod u plus c, which is returning the meaning of u back as a function in x. We've got that. Let's look out for this one. Be careful here. Let's have a look. What do we notice? Yes, it's a product of two things, but there's something wrong here. That's not quite the full derivative of this function up here. Okay, so we'll still let, and I think a better way rather than what they've got here, I'll just show you an alternative. When you see that, you say let u equal 1 take x squared. But then du by dx is neg 2x. Now rather than what the book's done, I'd like to do this. Neg a half du dividing both sides by neg 2 equals x. Now our integral, watch this, our integral x e to the 1 take x squared dx is equal to the integral of, okay, e 1 take x squared, but instead of our x, let's put in here neg a half du by dx. See, it's a slightly different way. In other words, get an expression for that when it's not the full derivative and slip it in there. Then we're back up to this one here anyway. This line here anyway. They put that in as a fitting in the derivative. I think it's better to write down the derivative, adjust it and isolate the term you want, and then go into u's, of course. So now this is the integral of e to the u du by dx, which is the integral of e to the u du, which is going to be integral of e is itself plus c, and then returning it. Oops, I've left out this neg a half in here, terrible business. Well, the whole story was about that. Neg a half, and therefore it's neg a half e to the 1 take x squared plus c. So you need to watch those where the product is not the full derivative of that other function. Okay, so watch it. You can look at the setting out here. It's the same idea from here down. It's just a matter of how you adjust the fact that we don't have the full derivative of neg 2x there. Okay, let's do another one. Okay, so what we've got here is cos cubed x times sine x. It's a product, so it's a candidate for reversal of the chain rule. So cos cubed x is cos x all cubed. So it is a function of that, and what do you notice? The derivative of cos is almost there. Remember, the derivative of cos is minus sine. So what we're going to have to do is to say, well, we'll let u be cos x. That's the function that's got another function done to it. So let u be cos x. Du by dx is minus sine x. So this is another one that needs adjusting. So this is u cubed. This is minus du by dx, because that's supposed to be negative sine x. Okay, and then we come to here. For forgetting these, some people cancel them. I don't like that because it's not really a cancelling situation. It's identifying that theorem, the reversal of the chain rule. So coming down here, treating u as a variable, it's u to the fourth on 4 plus c, and we've got our negative here. That's a property of the integral, isn't it? By taking it out the front there. And then we've got to return it to what u really means, which is cos x. So they're fairly tricky dickies, these little ones. So I would deal with this over here separately. I put this equal to the integral of 1 on sine x. Let's show the pieces. Show the pieces of the chain rule or function rule. And then you can see, that is the derivative of sine x. So let u be equal to sine x. Checking out du by dx equals cos x. So then encoding it, so it's 1 on u du by dx with respect to x, which is 1 on u du. It means we're only going to worry about reversing reciprocal function, which is ln mod u plus c, ln mod sine x, returning u. Do not answer in terms of u. It's something we've introduced as a part of a mathematical proof. Now I would tend to put these lines under each other and just adjust it and then return to the integral. You're setting out is important. If they say show that it's something, then you can't just do it by observation. A lot of people can, just seeing that go down to here, realising basically you can ignore that and you're only working with this if you like. Okay, so it is mentioned in the syllabus by inspection or by substitution. It's probably safest to check out the substitution, but see how good you are. Okay, here are some for you. Using substitutions to perform the integration. They're friendly in this question. They're telling you what u should be. The general rule is u is the function whose derivative is present. So I would identify u by seeing which one is the derivative of the other. Okay, so they're telling you in these early ones, but down here you'll have to identify for yourself what is the simple derivative or nearly the derivative of the other, and then that other is let u be equal to that. Okay, so sometimes the whole derivative will be present. Okay, derivative of that, or derivative of this whole thing rather, is 4x cubed, but over here the derivative of this function needs adjusting because the function down there I've underlined has a derivative of -2x and you've only got x, so you have to do a bit of a wiggling around there. So that's important to make sure you've got the whole derivative. There's not a negative or a half of it present or something like that. Okay, so a small set of problems here. It's important to do all of these, I think. Okay, so have a look at that and see what you think, particularly some in this one and down here. You might have to stop and think. You might have to actually let u equal and not try to do it by inspection in those cases. Okay, pause the presentation and have a go. I'll show you the answers now. And don't forget the c's. They're very, very important. The idea that when you integrate, you could have a whole family of functions all differing by a constant, which would all give the same derivative. Okay, so mark your work. There's a little bit more to do before we finish off integration and see some interesting applications with areas under curves and volumes of solids of revolution. So that's good fun. Right, well, at the moment, therefore, it's cheers from me, and I'll catch you a bit later.